Hello, we're back. We're talking about using the remainder theorem to determine equations. You can always use systems of equations, which is something that you've done in your past, to be able to determine function values. This one might be just a little bit easier once you get used to it. Remember, we're looking at the remainder theorem, so the polynomial can be expressed as p of x equals some quotient function times the thing you were dividing by, which is the factor, plus its remainder. And so one thing you might want to do is organize your work this way. You saw the work in the previous problem sort of done out without this table, so the table might just make it a little bit easier for you to organize and understand. First thing I'm going to do is I'm going to look at the value that I was given and understand its connection to not only the factor but the remainder. So if I have a -1, this is really what x equals -1. When I substitute that in, I get -3. That's the remainder. And so I can rewrite my function as the factor that I divided by a quotient function. And so again, this is not multiplication, but it's a quotient function. So I'm trying to keep these organized within the brackets just so it makes it a little bit easier to see and differentiate between multiplication. So this is my new polynomial function. Okay, when I use that, I can substitute into this, and so I should have p of 0 equals 0 plus 1 times the quotient function at 0 minus 3, because that's the original function, and when I got done with this equaled -2. 1 times a naught, and then I add the 3 to the other side, so because I'm out of room, my function at 0 is equal to 1, which is really just a remainder. Okay? And so now I can rewrite this in terms of this being a function. So the a of x is also a function that if I divided by a value, x plus 0, it also has its own quotient function with its remainder. Simplified, this is going to be x b of x plus 1. Okay, and this represents the quotient function of the quotient function. And so as you're layering these down, remember, if you divide a cubic by a linear, you're going to get a quadratic. If you divide a quadratic by a linear, you're going to get a linear divided by linear by a linear, you're going to get some sort of constant. And that's ultimately where we're trying to get ourselves down to here. And so I can rewrite my p of x in place of the a of x. I can put this new function, which is x b of x plus 1 minus 3. I come back over here and I go through the same thing. I substitute the -1 in, so p of -1 equals p of 1 equals -1, sorry. So I get on the outside 1 plus 1 is 2. X is 1 times the b of 1 plus 1 minus 3, and that equals -1. I simplify all this out, just out of space, but b of 1 is equal to 0. So this is actually a factor, which is really nice, but we'll come back to it in a second. So b of x could actually be represented by x minus 1 times some new quotient function, c of x, and so now I can rewrite p of x as its original x plus 1 with this quantity x times x minus 1 times c of x it had no remainder, so I can just write this plus 1 here and the minus 3 there. And we can do it one final time. So P of 2 equals, so 2 into here is 2 plus 1 is 3. 2 times 2 minus 1 times C of 2 plus 1 minus 3. When I get done solving all of this, you'll get C of 2 is equal to 1. This is our constant. So I took my 1, 2, 3, 4 points, third-degree polynomial. I divided it each time by a linear, and eventually you'll get down to the constant. So now I can rewrite this as C of x is the constant 1. And now I put this in my polynomial function. P of x is x plus 1, x minus 1 times 1 plus 1 minus 3. So we'll simplify this, x plus 1. This gives me x squared minus x plus 1 minus 3. I distribute this in, I'm going to get x cubed minus x squared plus 1x plus x squared minus x plus 1. That's all the distribution into that, minus 3. Simplify x cubed. I notice that I have a minus x squared, a plus x squared, a plus 1x, minus 1x. And so ultimately I'm just left with negative 2. And so that's your equation, and you'd find it the same way if you were using system of equations. And so keeping this organized can be really, really helpful as you extend yourself and your understanding of the remainder theorem. Thank you for your time.